Assalamualaikum and hi everyone. Today we would like to explain about spark ignition engine. So our group member is Ahmad Uwais Al-Qarani, me myself Muhammad Amza bin Muhammad Noor and Muhammad Nabil Hakim. Our dearest lecturer is Dr. Siti Ujila binti Masuri. So I will begin with the table of content. For the first one is description of the application of spark ignition engine. Second is explanation of fundamental principle of first law of thermodynamics related to spark ignition engine. The third one is explanation on fundamental principle of second law of thermodynamics related to spark ignition engine. And the last one is explanation on thermodynamics analysis involved in the spark ignition engine. Now, I will begin with the description of the application of spark ignition engine. First of all, a spark ignition engine, also known as a gasoline engine, it is an internal combustion engine that uses a spark to ignite a mixture of fuel and air in the combustion chamber. In thermodynamic terms, the spark ignition engine operates on the Otto cycle, which is a thermodynamic cycle that describes the functioning of a four-stroke spark ignition engine. The Otto cycle consists of four processes, which are intake, compression, combustion, and exhaust. The spark ignition engine requires a specific ratio of fuel to air to ensure complete combustion. The engine control unit (ECU) controls the air-fuel mixture by monitoring the sensors data such as the oxygen sensor and mass airflow sensor. Furthermore, the spark ignition engine also has a system to control the ignition timing called the Ignition Control Module (ICM) or Ignition Control Unit (ICU). Next, we will proceed to Mr. Uwais for further explanation.
Hi, Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Ahmad Uwais Al-Qarani bin Ahmad Fahmi and my matrix number is 212295. So right now I will explain to you about the first law of thermodynamics that involved in spark ignition engine. The first law of thermodynamics, also known as the law of conservation energy, state that energy cannot be created or destroyed, only transformed to one form to another. In the context of our project or our presentation, a spark ignition engine, the first law can be applied to the engine's fuel and air intake system, combustion process, and exhaust system. Consider a typical spark ignition engine operating at steady state. The energy input to the engine comes from the fuel and the air mixture that is combusted in the engine cylinder. The first law can be applied to calculate the thermal efficiency of the engine, which is the measure of how efficiency the energy from the fuel is converted into useful work. The energy input can be calculated as the sum of energy content of the fuel and the energy added by the air intake system in the form of air. The energy output from the engine can be calculated as the useful work done by engine on the crankshaft, which can be determined by measuring the torque and the speed of the crankshaft. Next, the energy conservation equation for the spark ignition engine can be represented as energy input is equal to energy output plus energy loss as waste heat. Like I said in the previous slide, this equation represents the first law of thermodynamics, which states that the total energy in a closed system must remain constant. In the case of spark ignition engine, the energy input to the energy comes from the fuel and the air mixture that is combusted in the engine cylinder. Thereby, the energy output is the useful work done by the engine on the crankshaft. Any energy that is not converted into useful work is lost as waste heat, which is expelled from the engine in the form of heat energy through the exhaust system. Mathematically, the energy input to the engine can be represented as the sum of energy content of the fuel and the energy added by the air intake system in the form of air. The energy output from the engine can be represented as the useful work done by the engine, which can be calculated from the torque generated by the engine and the crankshaft speed. And then, the energy loss as waste heat can be calculated as the difference between the energy input and the energy output, which can sum up with this equation: energy input is equal to energy content of fuel plus energy added by air intake system. And for energy output is torque times with crankshaft speed, energy loss as a waste heat. And for the energy output is torque times with crankshaft speed, and for the energy loss as the waste heat, we can calculate as energy input minus energy output. So it is important to note that this equation are simplified representation, and then the actual energy conservation in spark ignition engine will depend on several factors such as design, engine operating condition, and the fuel properties. Next is the mass conversion. In the conversion of mass in spark ignition engine, the mass of fuel and air that is thrown into the engine cylinder is converted into different form of mass, such as gases in the exhaust system, engine lubricant, and engine component that may wear or be damaged during operation. The mass of fuel and air that is thrown into the engine cylinder can be represented as the sum of the mass fuel and the mass of air. The mass of fuel can be determined by measuring the volume or weight by the weight of fuel consumed by the engine, while the mass of air can be determined by measuring the volume or density of the air that is drawn into the engine. During the combustion process, the fuel and the air mixture is ignited, resulting in the conversion of the mass of fuel and air into gases such as CO2 and water vapor in the exhaust system. Any unburned fuel and air will also be expelled from the engine in the form of exhaust gas. It is important to note that the mass of fuel and air that is drawn into the engine cylinder will not be equal to the mass of exhaust gases expelled from the engine. This is because some of the mass of fuel and air is converted into energy in the form of heat and work during the combustion process. This conversion of mass into energy can be described by the equation mass of fuel and air times with energy content of fuel and air divided by speed of light power of 2 equal to energy release during the combustion. This equation represents the famous equation derived by Albert Einstein, E equal to mc square root, which stated that the mass and energy are interchangeable, and the conversion of mass into energy result in an increase in the total energy of a system. Then, our vision to look at the whole spark ignition engine is E equal to Q minus W. The first law of thermodynamics can be applied to spark ignition engine to calculate the energy and work involved in the engine operation. The first law stated that the total of energy is in a closed system must be remain constant. In the case of spark ignition engine, the closed system includes the fuel and air mixture in the engine cylinder, the engine component, and the exhaust gas expelled from the engine. The energy work involved in the engine operation can be represented as E equal to Q minus W, where E is the change of the total energy in the system, Q is the heat energy added to the system, and W is the work done by the system. In the context of a SPE, spark ignition engine, Q is represented as the heat energy generated by the combustion of the fuel and air mixture in the engine cylinder. W represent the useful work done by engine on the crankshaft. E represented the energy lost as a waste heat, which is expelled from the engine in the form of energy through the exhaust system.
Assalamualaikum, and my name is Muhammad Nawal Hakim Rahim. My matrix number is 210406. Today, I will present about the explanation of fundamental principle of second law of thermodynamics related to spark ignition engine. So, in second law of thermodynamics, normally heat transfer from hot to cool, but to transfer heat from low temperature to high temperature, it needs amount of energy to make it possible. It is natural process that irreversible. Spark ignition use thermal energy to mechanical energy. There is no heat engine with 100% of efficiency. About 2/3 of the gasoline used to power an automobile is converted into heat. Process of internal combustion. First is intake. Gasoline and air is mixed together in a cylinder that expands against a piston. Second process is compression. A crankshaft then moves the piston upward and compressing the mixture. The third process, ignition. At maximum compression, a spark plug fires, igniting the gasoline air mixture and increase temperature cylinder. 4. Expansion. Hot mixture QH expand rapidly. 5. Exhaust. The exhaust gases QL are ejected at lower temperature as the piston and the process repeats.